Bismillahirrahmanirrahim. Dear students, today we are going to discuss Julia olefination reaction, which is modified by Lithgow and Kosiansky. This reaction is also basically for the formation of alkene from aldehydes using some another reagents, as we have discussed in the previous lectures for the olefination from aldehydes like Wittig reaction and etc. The key concepts of today's lecture is the introduction to Julia olefination reaction and the introduction to the different modifications made by the scientists like Lithgow, S.A. Julia and Kosiansky. Then the discussion of the reacting species including aldehydes, ketones and bases, and then sulfones and the solvents, the isolytic agents used for this reaction, and in the end there is given the general mechanism of the reaction along with two types of catalysis including sodium amalgam, sodium mercury, and the other is samarium iodide. So this is the total concepts or points which will be discussed in today's lecture. Julia olefination reaction. First in 1973, M. Julia and J. M. Paris worked on this and discovered this reaction in which sulfones are treated and converted into beta siloxy sulfones and which are further reduced and elimination occurs to form alkenes. In 1978 and 1980, B. Lithgow and P.J. Kosiansky modified it, and but this modification was not too much prominent. In 1985, 96, 98, 99, Kosiansky further worked on this reaction and many modifications were made, which also changed the path of the reaction and also affected the yield of the reaction, rate of the reaction. Sulfones are first converted into sulfonyl stabilized carbonyls, and these carbonyls are then reacted with carbonyl compounds to form alkene. The elimination step in the alkene is performed in different ways, and the modifications made in Julia olefication reaction differ in this step. First, the acylation followed by sodium mercury or samarium iodide reaction. The Julia Lithgow olefination is termed in this modification, but the elimination by Smiles rearrangement is termed as Julia Kosiansky reaction. Both of these modifications are prominent in this reaction. So this Julia olefication reaction is also basically the conversion of aldehydes and ketones into alkene. The general reaction is shown here, in which you can see the sulfones are treated with base and aldehyde and acetic anhydride to form beta siloxy sulfones, and these are further reduced by sodium mercury in the presence of methanol to form alkene. If we revise the history of the olefination of carbonyl compounds, then you remember that different carbonyl compounds, aldehydes or ketones, were treated with different reagents to form alkenes, cis-alkene or trans-alkene, that is E-alkene or Z-alkene. Here you can see in this structure a general reaction is shown in which X is generalized, and this X can be in case of Wittig reaction it was trialkyl phosphine, In case of Horner-Witting, this was dialkyl phosphine oxide. In case of Horner-Wurtzman-Amos, this was phosphonates. In case of Peterson reaction, it was trialkyl silicon. Similarly, Johnson reaction, similarly classical Julia reaction, which used aryl sulfones, and modified Julia, which used heterocyclic sulfones. So these are the different reactions which are involved for the olefination of carbonyl compounds by using different reagents which differ in the stereochemistry of the product and rate of reaction and yield. First modification was made by Julia Lithgow, and so this modification is termed as classical Julia Lithgow olefination reaction. The basic Julia reaction is almost just similar to that of this as which we are going to discuss, that is Julia Lithgow olefination reaction. Only the difference that the further modifications or plus minus points have been added or removed by Lithgow in the Julia reaction, and overall the reaction remains almost the same which was presented by Julia first time. So this olefination reaction has the following steps. The first step is the addition of alpha metallated phenyl sulfone to an aldehyde and ketone. Alpha metallated phenyl sulfone means it was phenyl sulfone which was treated with a base to convert into a nucleophilic carbanion. That carbanion makes the salt with the positive part of that base or metal, so this salt form of the sulfone is called alpha metallated phenyl sulfone. Alpha is used here because the acidic proton which is removed from the sulfone is from the alpha position of the sulfone, so this is called alpha metallated phenyl sulfone. This is then treated with aldehydes and ketones to form an alkoxide ion. And second step is the acylation of the resulting beta alkoxysulfone, or it should be said that beta alkoxide sulfone. The purpose of acylation is that the hydroxide O minus alkoxide ion is converted into a good leaving group, because O minus is difficult to leave from the molecule, so it is converted into acylated product or acyloxy group, which is easily removed from the main part of the molecule, and we get alkene at the end of the reaction through elimination. Third step is the reductive elimination of the beta acyloxy sulfone, in which acyloxy group is removed from the sulfone by the single electron donor and species, or we can say SET, single electron transfer species, and we get the desired alkene. The basic features of this Julia Lithgow olefination is it has high E stereoselectivity, that is a selectivity for the E isomer. E mean the groups at the opposite sides. This E selectivity is further depending upon the branching present on the alkyl group, which is going to be the converted into alkene, and this branching increase in branching increases the E selectivity. E selectivity is increased with increasing the chain branching around the newly formed double bond. And third feature is that the relative stereoselectivity in the intermediate, that is beta acyloxy sulfones, does not influence the geometry of the alkene product. That is, the geometry of the alkene product does not depend upon the stereochemistry of these species. The reason is that the last step of single electron donation or single electron transfer moves in such a way that we preferably get the E product and not Z products. Here you can see the general overall reaction for this classical Julia Lithgow olefination reaction. That alkyl phenyl sulfone reacts with the base to form alpha metallated alkyl phenyl sulfone as a salt. This acts as a nucleophile through carbon, and carbon attacks on the carbon of the carbonyl group of the ketone, and we get the next product, which is beta alkoxy sulfone or alkoxide. In the next step, this beta alkoxy sulfone is treated with acyl halide for the process of acylation of at this oxide ion of this beta alkoxy sulfone. It becomes a good moving group. And in the last step, it is treated with the sodium mercury amalgam in the presence of ethanol, and we get the alkene, and which is preferably E-alkene. Here the different groups which are present in this reaction. R1 can be hydrogen alkyl or aryl group. R1, which is present in this alkyl phenyl sulfone, it can be hydrogen, it can be alkyl group, it can be aromatic aryl group. R2 and 3 of the ketones can be hydrogen, alkyl, aryl or alkenyl group. That is, this reaction is favorable for the aldehydes, favorable for the ketones, or alpha beta unsaturated ketones or aldehydes. And R4 is from the acylating group, and this also can be alkyl group or aryl group. X is can be halogen, can be bromo, halogen like chlorobromo, and are good living group like acetate, ion, etc., as in the form of anhydride. If we use anhydride, then the living group is OCOCH3, and if we use acyl halide like acetyl chloride, then the living group is chloro, and so on. So this is the overall reaction of classical Julia Lithgow olefination. As we have discussed the Julia Lithgow olefination reaction, it basically consisted of three steps. That first step was the preparation of carbanion and the reaction with aldehyde or ketone to form an alkoxide ion. This was first step, which requires one pot. Then the second step was the reaction with acetyl chloride or acetic anhydride, that is acylation. It is termed as the second step. And the product obtained from this step is then treated with sodium mercury amalgam in ethanol. This is the third step. So overall the reaction was consisted of three steps. But the modification made by S.A. Julia was to one pot modification. That is, the overall all of the reactants were treated in such a way that we get a one pot synthesis. That we have not to one pot mean all the reactants are added in one flask with the intervals of time with the according to the procedure which is obtained, but only one pot, one flask is used, and we get finally the product. And if it is not one pot, then it means that one step is completed and the product is obtained, separated, purified. Then the second step is moved on, the found product is again filtered out, purified, extracted, etc. And then the third step, so it requires more than one pot. One pot synthesis is too simple, or you can say it is beneficial in this sense that it keeps much time, less time, and also there are chances that we can get maximum yield, and there are less chances for wastage of chemicals. In this one part synthesis of S.A. Julia, alpha metallated heteroaryl sulfones are added to carbonyl compounds, and the difference, first difference of this modification and the last classical step is that this modification use heteroaryl sulfones, and the last classical Julia reaction uses phenyl sulfones. The intermediate beta alkoxy heteroaryl sulfone quickly undergoes to Smythe's rearrangement and we get the alkene. That is, do not have to add to move to acylation. We do not need to move towards the sodium mercury amalgam reaction. Simply the formed alkoxide moves towards the rearrangement, that is called Smythe's rearrangement, and we get the alkene. This unstable intermediate, that is this intermediate beta alkoxy heteroaryl sulfone, which quickly goes to Smythe's rearrangement, and the breakage of heterocyclic bond with sulfur of sulfone. That is, in this rearrangement the bond present between the heterocyclic carbon and the sulfur of the sulfone is broken, and we get an intermediate which is called sulfinate salt. That is unstable intermediate which decomposes to form the alkene. All this is happening in one pot. Here is the main point, that the different heteroaryl sulfones do not work with the same pattern. That is, they have different yields, they have different stereoselectivities, they have different rates of the reactions. So varying the heterocyclic group attached to the sulfone, we can get change the yield, change the stereochemistry, and change the rate of the reaction. The further modification is known as Koensky olefination modification. This modification is basically just similar to, as we have discussed, SA Julia olefination reaction. The difference is in the aryl group which is used, and the result is that the aryl group used by Koensky was PT sulfone, that is 1-phenyl 1H tetrazole 5-yl sulfone, which was treated, and we obtained non-conjugated 1,2-disubstituted alkene with high E selectivity. As we have discussed that the stereochemistry for the SA Julia was not specifically, there was a mixture, but here we obtained the product with E selectivity, and that was also only possible if there was no significant electronic or steric biasness in the reaction. Secondly, for the preparation of conjugated 1,2-disubstituted Z alkenes, the use of allylic or benzylic TBT sulfones, TBT means 1-tertiary butyl 1H tetrazole 5-yl sulfones, was recommended. That is, by using PT sulfone we get E selective alkene, and by using TBT sulfone we get Z alkene, conjugated 1,2-disubstituted Z alkenes. So the change of this aryl group has remarkable effect on the nature of the product, yield, etc. Here are the structures given for 1-phenyl 1H tetrazole 5-yl sulfone and 1-tertiary butyl 1H tetrazole 5-yl sulfone. The nomenclature of this compound can be discussed for your information, that this ring is 5-membered. 4 members are nitrogen and 5th is the carbon. So this is 5-membered ring in which 4 nitrogens are present. If you number this ring only, then the number 1 is given to the heterocyclic atom. In a heterocyclic compound, the number 1 position is given to the heteroatom, and here there are more than one number of heteroatoms are present. Then we number in such a way that they get the minimum number, and you will start one position from the 2 terminal of 2 terminals nitrogen present in this ring. Terminal mean 2 nitrogens are inside and 2 nitrogens are at the corners in this row of 4 nitrogens. You will number 1 to that nitrogen which is attached to phenyl ring, or you will number the other nitrogen. As the substitution gives priority, so the number 1 is given to that nitrogen which is attached to phenyl. So it is also termed as 1-phenyl. Position of the phenyl group is 1-phenyl. And 1H tetrazole, tetra means 4, azo is a symbol for nitrogen, and ol for 5-membered ring. As this is 5-membered ring, so called O ol, and A is for nitrogen, and tetra for 4 nitrogen. So this ring is named tetrazole overall. 5-yle, fifth position, that is here the carbon from which it is going to be act as a group. So this is termed as 5-yle, and sulfone is the general class of this compound. So overall this compound is named 1-phenyl 1H tetrazole 5-yle sulfone. 1H mean one hydrogen is present at first nitrogen, which is not here present due to the substitution with phenyl here in this case, but is written in the name of the compound. Similarly, the name of the other group, that is 1-tertiary butyl 1H tetrazole 5-yle sulfone, is given. This is the overall reaction, which is one part synthesis modified by S. Julia and further worked on it by Kosienski, olefination. Here you can see the heterocyclic aryl sulfone is first converted into alpha metallated form, then it is reacted with aldehydes or ketones to form beta alkoxysulfone, and that beta, here you can see the name why it is termed as beta, because the alpha position and beta represented at beta position this group is present, so named as beta alkoxysulfone. Beta alkoxysulfone is further converted into the alkene through Smail's rearrangement. The mechanism is not given here. We are discussing only the general introduction to these rearrangements. In the next lecture we will completely discuss the mechanism for these rearrangements. And we get the product. The byproduct is the metal salt of the aryl group. Here the R1 group, which is present in the sulfone, can be hydrogen alkyl or aryl. R2 has no specification, also it can be alkyl, aryl or alkenyl. And the HET, heterocyclic aryl group, which is attached to the sulfone, and this hetero can be benzothiazole 12-BT, which is shown here, and can be pyridine 2-yle or can be 1-phenyl 1H tetrazole 5-yle PT, which was shown by Konsky for the same reaction. So this is the overall reaction which was the modified by the Julia, and we get one part synthesis of alkene. First reacting region in this reaction is sulfone. Sulfones are organosulfur compounds. In this in the sulfone, sulfur is attached to two double bonded oxygen atoms. Here you can see one is written as sulfonic acid, which contains S double bond O, which is attached with R and OH. But if S double bond O is attached with two alkyl groups, then this is known as sulfones. Here the R group can be different alkyl, phenyl, aryl groups, R alkyl groups, etc. But one thing which is the basic necessary condition for this reaction is that one group among these two R groups should bear alpha hydrogen for the production of carbanion with the help of a base, and this carbanion is the initiator of the reaction which moves into the further steps. This carbanion is also known as sulfonyl stabilized carbanion, because you can see here the negative charge of this carbon is resonating towards the sulfur, and the double bond is broken and moves towards the oxygen, and in second resonating structure this negative moves back, and double bond of the other S double bond O is broken, and oxygen minus is created. So this anion has three resonating structure. In this way you can say this anion is much stabilized by the resonance due to the presence of this sulfonyl group. Next we discuss here the synthesis of sulfones. Sulfones are synthesized by different methods. Here is discussed one of the most important, or you can say most familiar method, that thiols. are compounds bearing this is group is also known as mercapto group. This mercapto group or thiol are converted into sulfides by the reaction with halides to silates or triflate in the presence of base, or by the reaction with alcohols in the presence of these catalysts and solvents. These sulfides are further oxidized into sulfone. This oxidation takes place in two steps. In first step, S sulfide is oxidized to S double bond O, and in the second step the S double bond O is further oxidized to S double bond O, and we get the compound sulfones. Here are the regions shown which can be used for the oxidation purpose of the sulfide to get the sulfones. Any one of can be used for this purpose. But all of these can oxidize, but the yields and the rates are different for each region. Next reacting region is aldehyde or ketone, which is treated with the sulfones. The aldehydes and ketones both can be used, and as we know, aldehydes are most reactive due to less steric hindrance, and so this high reactivity makes the great use of aldehydes for the olefination reaction instead of ketone. But ketones are also used. There are many examples in which ketones are used to synthesize the alkenes. One of the step is acylating. After reaction with aldehyde or ketone, the next step is the acylation of the region, and this is done by acylating agent. The different acylating agents are used for this purpose. Acylation is basically used to convert the alkoxide intermediate into a stable intermediate with good leaving group. Because at the time of elimination this O minus has to be eliminated. This O minus has been created from the aldehyde carbonyl, and as it is not a good leaving group in this form O minus, so it is converted into a good leaving group by treating with an acylating agent. For acylation, acetic anhydride, acetyl chloride, benzoyl chloride, benzoic anhydride can be used. Here are the structures given for all of these regions, and most of the time for acylation, acetic anhydride or acetyl chloride are used due to their high reactivity. First step of this reaction is the reaction of sulfone with the base to create a carbanion, and the different bases used for this purpose are N-alkyl lithium, especially N-butyl lithium, lithium diisopropylamide, also termed as LDA, sodium bis trimethyl silylamide, lithium bis trimethyl silylamide, or potassium bis trimethyl silylamide. Cesium carbonate, potassium carbonate are also used. The different solvents involve dimethoxyethane and tetrahydrofuran. These two are basically aprotic solvent which are used here. This is the overall reaction mechanism of this olefination, that first sulfones are treated with alkyl lithium as a base, and we get carbanion. This carbanion is acting as a nucleophile, attacks on the carbonyl carbon of aldehyde or ketone, and we get an alk oxide ion. This alk oxide ion is treated with an acylating agent to get a good removing group, good leaving group. This region intermediate is treated with sodium mercury amalgam in the presence of ethanol, and through single electron transfer mechanism we get the alkene. This is the overall mechanism, and now we shall discuss each step of this mechanism in detail. Here is the mechanism for Julia litho reaction through the sodium amalgam. As we discussed earlier, that it can be moved through sodium amalgam or samarium iodide, and first we discuss with the sodium amalgam, then general reaction with samarium iodide. Sodium amalgam, if we use sodium amalgam for the reaction medium, then here you can see the sulfones are treated with the acyloxy substituent or group which has been synthesized after previous steps, which has been eliminated is here. This acyloxy beta acyloxy sulfone is treated with sodium mercury amalgam in methanol. The basic reagent which has been created due to the reaction of sodium with methanol is sodium methoxide, which acts as a strong base. This is known as strong base because the methoxide ion easily gets the proton from any species and becomes methanol. So due to its large affinity for abstracting or attracting the H plus proton, it is termed as a base. So here this base abstracts the proton, and the double bond moves towards the sigma bond between carbon and hydrogen moves towards the dead bond between alpha and beta carbon. Here you can see this group is this hydrogen adjacent to the sulfone in alpha position of the sulfone. The hydrogen is abstracted only, but not that hydrogen which is present at beta. Why this is? Because you can explain the electron with drying group sulfone is present here, and due to strong electron with drying group, this hydrogen is more acidic as compared to that which is present at beta position. So this alpha hydrogen is omitted, and we get a double bond between alpha and beta carbons, and at the same time the acyloxy group is removed as it is a good leaving group. In the next step we get an alkene after the removal of acyloxy group. It is also termed as vinyl sulfone. Vinyl sulfone now is treated with sodium through single electron transfer mechanism. Through this we will discuss in next lecture in detail what is meant by single electron transfer and what is its overall mechanism of for transferring of electron, and what are the results after this transferring of electron. Here I am going to generally discuss this reaction. So this one electron in the valence shell of sodium attacks on the oxygen, and the double bond moves towards the sulfur, and you see the product in which sulfur bears a radical, that it has becomes a radical. Sodium has become a cation after losing one electron, which is now attached to the oxygen, which bears a negative charge. Here the arrow from sodium is given to oxygen because it is single-headed arrow. Single electron is coming towards the oxygen, and the pi bond is broken. Pi bond is made by two electrons, one from oxygen, one from sulfur. The electron from sulfur is moved toward the sulfur, and we get sulfur radical in the product. And the electron from oxygen comes towards the oxygen, and it gets one electron from the sodium, so it is negatively charged, and sodium positively charged is attached with it, making it in salt form. The sulfur is present as a radical. In the next step, the bond present between carbon and sulfur is broken in such a way that we say this breakage as homolytic breakage. This homolytic breakage in such a way that the one electron moves towards the carbon and one electron moves towards the sulfur. As the electron moves towards the sulfur, it becomes its valency is satisfied, and we get a simple compound in salt sulfone in the form of salt. and the other product is a radical, also called vinyl radical. Here you can see two forms. In first form of vinyl radical, R1 and R2 are present at E position, but in the second form R1 or R2 present at Z position, that is on the same side. Here the double added arrow show that these both are equilibrating, but the thermodynamically favorable product is the trans means R1 and R2 are at opposite positions, that is E isomer. So the product formed is according to this vinyl radical, in which R1 and R2 are at opposite positions, and next again sodium comes and transfers one electron to this carbon already containing one electron, and we gets a anion. This anion gets a proton from the methanol, which is present as a solvent, and it is converted into simple neutral E alkene, and the methoxide produced as a byproduct is counterbalanced by the sodium ion, which was produced in this step also. So this is the overall reaction mechanism which proceeds through the sodium amalgam. Here is the second mechanism with samarium iodide, SMI2. Samarium is from F block elements and also from lanthanide series. Here the reaction shows that samarium SMI2 at the first step goes through single electron transfer reaction to this acetyloxysulfone, and this single electron is obtained by the sulfur, and the sigma bond present between alpha carbon and sulfur is also broken. The electron from this bond is also moved toward the sulfur, and sulfur gets the neutral species. Neutral mean its lone pair is counterbalanced, and it is attached with samarium iodide also. In this samarium iodide, in this sense that SMI2 after losing one electron becomes a radical cation, and this species SO2 after gaining one electron becomes a radical anion. This cation and anion are attracted with each other and form a stable compound, a molecule. The electron from this sigma bond of alpha carbon and sulfur was moved towards the carbon, and we get a free radical at this carbon. This free radical is termed as secondary alkyl radical. As you have seen that in case of sodium mercury amalgam there was formed a vinylic radical, but here in this case we get a secondary alkyl radical. Alkyl radical is because there is no double bond or triple bond, simple alkyl groups are attached, and secondary because this radical carbon is further attached to two carbon, one in the form of R1 and second in the that carbon which was beta in the last step, and here it is further attached to acetyloxy group and R2 group. So due to these two carbons, this is termed as secondary alkyl radical. In the same pattern as we have discussed for sodium mercury vinyl radical, they were equilibrating between two forms, that is cis and trans. Similarly, the secondary alkyl radical is also equilibrating between two states, that is E form and Z form. E form mean R1 and R2 are on the opposite side, and Z form mean R1 and R2 groups are on the same side. And on the same ground, on the same basis, the thermodynamically favorable state was the trans form, that is R1 and R2 are on the opposite side, and this moves towards the next step. Next step then also is the again some single electron transfer with samarium iodide, and we get the anion in the similar fashion as we obtained with sodium mercury. This anion moves towards the carbon-carbon single bond and makes it double bond, and the acetyloxy groups is removed here as a leaving group. So we get the alkene, and also this alkene is E-alkene preferably. So this is the overall mechanism with respect to samarium iodide. This is all about of today's lecture. and in next lecture we shall discuss the start from the complete mechanism, and then we shall discuss the mechanism of the reaction step by step, and then in the end we shall also discuss the mechanism of different modifications made in this Julia reaction, and also some synthetic applications of these reactions in the practical field, practical market of medicines, etc. So it is this is all about for today's lecture, and thanks.